The night of March 9th, 1943, somewhere over the Ruhr Valley, Germany. Oberleutnant Klaus Fischer sat in the cramped cockpit of his Heinkel, He 111 bomber, watching the scattered clouds below drift across the landscape like torn fabric. Perfect conditions, he thought. The darkness that blanketed Germany's industrial heartland had always been their greatest protection against British night fighters. For 2 years, Luftwaffe bomber crews had operated under a simple principle. If you couldn't see the enemy couldn't see you. Visual interception at night required searchlights, ground control, and extraordinary luck. Most German crews returned safely, their missions completed under the cover of absolute darkness. But something had changed in recent weeks. Bomber crews were disappearing, not in the spectacular fashion of daylight raids where flak and fighters carved visible paths of destruction through formations. These losses were different. Aircraft simply failed to return, vanishing into the night without radio calls, without witnesses, without explanation. Fischer had heard the rumours in the ready rooms. British night fighters were finding German bombers in complete darkness, in weather conditions where visual interception should be impossible. Some crews whispered about new British technology, but most dismissed such talk as defeatist speculation. The Luftwaffe had the finest radar systems in the world. Everyone knew that. If Germany possessed technological superiority, how could the British achieve what German science declared impossible? Fischer's radio crackled with routine check-ins from other bombers in the loose formation scattered across 50 kilometers of airspace. His bombardier, Feldwebel Hans Krebs, called out navigation updates as they approached their target, a synthetic oil plant near Essen. Everything seemed routine. The darkness remained absolute. No searchlights swept the sky. No flak bursts marked their altitude. They were invisible, protected by night itself. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Then Fischer's rear gunner, Unteroffizier Wilhelm Braun, screamed into the intercom. "Fighter! Fighter! Closing from below and behind!" The words barely registered before cannon fire ripped through the Heinkel's fuselage. 20mm shells tore through aluminum skin, shredding hydraulic lines and severing control cables. The bomber shuddered violently. Fischer fought the controls as the aircraft rolled inverted. Through his canopy, he glimpsed the silhouette that had killed his aircraft, a twin-engine Beaufighter, already banking away into the darkness from which it had emerged without warning. Heinkel was dying. Fire spread through the fuselage. Fischer gave the order to bail out, his voice surprisingly calm despite the chaos. As he struggled free of his harness and prepared to jump, one thought consumed his mind. How had that British fighter found them in total darkness? They had received no warning from ground stations, seen no searchlights, detected no aircraft until the moment of attack. The British pilot had positioned perfectly for a textbook interception, approaching from the blind spot beneath and behind where German defensive guns couldn't engage. This wasn't luck or chance encounter. This was precision targeting that should have been impossible in conditions of absolute darkness. Fischer survived the parachute descent and spent the rest of the war in a British prisoner of war camp. During interrogation in the following days, he learned the answer to the question that had haunted him during those terrifying seconds before he abandoned his dying aircraft. The British had developed airborne radar systems that could detect and track aircraft in complete darkness and through solid cloud cover. The technology operated at wavelengths German warning receivers couldn't detect, providing British night fighters with capabilities that rendered darkness meaningless as a defense. German bomber crews had been flying missions believing they were invisible, protected by night. In reality, they had been illuminated on radar screens, tracked with precision, and hunted by fighters equipped with electronic eyes that saw through darkness as clearly as daylight. The transformation from confidence to comprehension would take months for German leadership to fully understand. But by March 1943, the evidence was accumulating in ways that could no longer be ignored. British night fighters were achieving interception rates that defied explanation through conventional tactics alone. Something fundamental had changed in the technological balance of night warfare. What German scientists discovered when they finally examined captured British airborne radar equipment would reveal a gap in understanding so profound that it shattered German confidence in their technological superiority and exposed vulnerabilities that no amount of tactical adaptation could overcome. The story of how Germany came to understand British airborne radar capabilities is inseparable from the broader narrative of radar development during World War II. Germany had pioneered military radar in the 1930s, deploying operational systems before Britain. The Freya early warning radar, operational by 1938, could detect aircraft at ranges exceeding 100 kilometers. The Würzburg precision tracking radar, introduced in 1940, provided accuracy sufficient to direct night fighters and anti-aircraft fire. By 1941, German radar formed an integrated air defense network called the Himmelbett Line, stretching from Denmark through the Low Countries and France. This system combined early warning radars, precision tracking radars, searchlight batteries, and night fighter control to create what German commanders believed was the most sophisticated air defense system in existence. German confidence in radar superiority was not mere propaganda. The Würzburg radar represented sophisticated engineering using conical scanning techniques that provided angular accuracy of approximately 0.2 degrees in azimuth and 0.3 degrees in elevation. The system could track individual aircraft at ranges exceeding 40 kilometers, sufficient to vector night fighters to within visual range of bombers. The larger Würzburg Riese variant, with its 7.4-meter parabolic antenna, extended maximum range to 70 kilometers and provided the precision accuracy needed for direct gun laying without optical confirmation. By 1942, approximately 1,500 Würzburg systems were operational across German-controlled territory, forming the backbone of an air defense network that had inflicted severe losses on RAF Bomber Command. German night fighter tactics exploited this radar network through a system called Himmelbett, or four-poster bed, referring to the geographic coverage zones. Each zone, roughly 30 kilometers across, contained a Freya early warning radar, 2 Würzburg tracking radars, a searchlight battery, and dedicated communications, linking these elements to a night fighter control center. As RAF bombers approached German territory, Freya detected the formation at long range. Controllers vectored available night fighters toward the threat. Once bombers entered a Himmelbett zone, one Würzburg radar locked onto the bomber, while a second tracked the assigned night fighter. Ground controllers provided running commentary, directing the fighter to intercept position. The night fighter crew, using this ground-controlled interception guidance, closed to within approximately 200 meters, the maximum range at which visual identification was possible on dark nights. The fighter pilot then completed the intercept visually, closing to firing range. This system worked. Through 1941 and 1942, German night fighters achieved steadily increasing success rates. Major Helmut Lent, one of Germany's most successful night fighter pilots, credited the ground control system with most of his eventual 113 confirmed victories. The integration of radar, communications, and tactical procedures represented sophisticated air defense doctrine that British bombers paid for in mounting losses. By mid-1942, RAF Bomber Command was losing approximately 4% of aircraft dispatched on major raids, an unsustainable rate that threatened to make strategic bombing ineffective before it could influence the war's outcome. But the German system had fundamental limitations that arose from the technology itself. Würzburg operated at 53 centimeter wavelength, chosen because German vacuum tube technology could generate sufficient power at that frequency using established components. This wavelength required antenna systems measured in meters to achieve useful resolution. The Würzburg's 3-meter parabolic dish was the minimum size needed for acceptable tracking accuracy. The Würzburg Riese's 7.4-meter antenna was a transportation and deployment challenge, typically mounted on railway flat cars. More critically, the long wavelength limited precision. Angular accuracy of 0.2 degrees translated to approximately 140 meters of lateral error at 40 kilometers range. This was acceptable for vectoring night fighters to visual range, but it meant ground controllers couldn't provide pinpoint interception guidance. The final attack phase required visual acquisition by the fighter crew, which was only possible on relatively clear nights at ranges under 200 meters. German airborne radar faced similar wavelength constraints. The Lichtenstein FUG, 202 airborne interception radar, introduced operationally in mid-1942, operated at 61 centimeter wavelength. The system required the matrace antenna array, 32 dipole elements arranged in a complex framework mounted on the fighter's nose. This array created significant aerodynamic drag, reducing aircraft speed by 20 to 30 kilometers per hour. Despite this performance penalty, Lichtenstein provided only moderate detection capabilities. Maximum range against bomber-sized targets was approximately 4 kilometers under ideal conditions, often less in practice. Minimum range was roughly 200 meters, creating a dangerous blind spot where the radar lost contact before visual acquisition was possible. The system worked, allowing night fighters to locate bombers independently of ground control, but its limitations were apparent to every pilot who used it. The British had faced identical technological constraints in their early radar development. The chain-home early warning system used wavelengths between 10 and 13.5 meters, requiring antenna towers over 100 meters tall. The original airborne interception radar, AI Mark IV, operated at 1.5 meter wavelength and required complex antenna arrays that barely fit inside Bristol Beaufighter fuselages. Like German systems, British early radar was effective but limited by the long wavelengths that available vacuum tube technology could generate with useful power levels. What British scientists achieved between 1940 and 1943 was a technological breakthrough that transcended these fundamental limitations. The development of the cavity magnetron, a device capable of generating enormous microwave power at centimetric wavelengths, enabled an entirely new generation of radar systems with capabilities that longer wavelength technology simply could not match. A radar operating at 9.1 centimeter wavelength with 10 kilowatts of peak power could detect aircraft-sized targets at useful ranges using an antenna barely 30 centimeters in diameter. The same antenna aperture at 50 centimeter wavelength would provide almost no useful range or resolution. The physics were inescapable. Shorter wavelengths enabled dramatically improved resolution with far more compact antennas. Britain had deployed the first generation of centimetric airborne interception radar, designated AI Mark VIII, on Bristol Beaufighters and de Havilland Mosquitoes, beginning in mid-1942. These systems used cavity magnetrons, operating at approximately 9.1 centimeter wavelength. The transmitter was compact enough to fit in the fighter's fuselage. The antenna, a parabolic dish just 71 centimeters in diameter, was mounted in the aircraft's nose, replacing the complex Yagi array that earlier radars required. Performance was revolutionary compared to previous generation systems. AI Mark VIII could detect bomber-sized targets at ranges approaching 8 kilometers, double the detection range of German Lichtenstein. More critically, the centimetric system maintained tracking at much shorter ranges, closing the minimum range gap that plagued longer wavelength radars. British night fighter crews could now acquire targets at longer ranges, track them continuously through the interception, and maintain radar contact until visual firing range was achieved. The tactical implications were profound. British night fighters no longer depended entirely on ground control interception to position them near enemy bombers. With AI Mark VIII, they could patrol assigned areas, detect bombers at useful ranges, and complete interceptions independently. The radar's superior resolution allowed crews to distinguish individual aircraft in formations. The narrow beam width provided accurate bearing information. The system was reliable, with production units manufactured to consistent specifications rather than hand-tuned laboratory prototypes. By early 1943, RAF Fighter Command was equipping Mosquito night fighter squadrons with AI Mark VIII at an accelerating pace, transforming their capabilities in ways that German bomber crews were beginning to experience with lethal effectiveness. German intelligence in the early 1943 possessed fragmentary indications that British night fighter capabilities had improved but lacked definitive evidence of revolutionary technology. Luftwaffe bomber crews reported encounters suggesting British fighters could operate in conditions where visual interception should be impossible. Loss rates over Britain were climbing steadily. Tactical analysis suggested British night fighters were achieving higher interception rates than ground control efficiency alone could explain. Some intelligence officers speculated about improved radar, but German technical experts insisted that compact, high-power centimetric radar remained beyond practical military applications based on fundamental physics and engineering constraints. This confidence in German technological understanding was about to be shattered by a series of captures that would force comprehensive reassessment of British capabilities and German vulnerabilities. The first critical evidence arrived not through deliberate intelligence operation, but through battlefield accident and German signals intelligence that assembled seemingly disparate data points into a disturbing picture. Throughout late 1942 and early 1943, German signals intelligence intercepted unusual radar emissions from British aircraft operating over Germany and occupied Europe. The transmissions were brief, pulsed signals at frequencies around 3 GHz, corresponding to wavelengths near 9 centimeters. German radio engineers who examined the intercept reports faced immediate theoretical problems. Generating useful power at such frequencies violated German understanding of practical limitations. Germany's most advanced radar research had explored frequencies up to approximately 600 MHz, corresponding to 50 centimeter wavelengths. Beyond that frequency, power output declined rapidly, according to German experimental data and theoretical models. 3 GHz seemed impossibly high for military radar applications requiring kilowatts of transmitter power. The intercepts were initially dismissed as measurement errors or possibly electronic countermeasures designed to confuse German radar operators. Some analysts suggested the signals might be interrogation transmissions, communicating with ground beacons rather than true radar emissions. The possibility that British aircraft were carrying operational radar systems generating these frequencies seemed to contradict established physics as German researchers understood it. If British engineers had solved the high-frequency power generation problem, it would represent a breakthrough of extraordinary significance, potentially rendering German radar systems obsolete. The truth arrived in fragments through multiple sources that German intelligence only gradually assembled into comprehensive understanding. On May 3, 1943, a Bristol Beaufighter from 604 Squadron RAF force landed near Rotterdam after sustaining battle damage during an intruder mission. The aircraft was captured largely intact. German recovery teams found radar equipment unlike anything in German experience. The rotating scanner dish mounted in the nose was barely 70 centimeters in diameter, far smaller than antenna arrays required for German airborne radar. The electronic chassis contained components operating at frequencies German equipment couldn't match. Most significantly, the transmitter section housed a magnetron generating enormous microwave power at 9.1 centimeter wavelength, precisely matching the mysterious emissions German signals intelligence had been tracking. General-Leutnant Wolfgang Martini, chief of Luftwaffe, signals intelligence and radar development, ordered the captured equipment transported immediately to Telefunken research laboratories in Berlin under maximum security. Martini understood that this capture might provide answers to questions that had been troubling German commanders for months. If British night fighters possessed radar systems superior to German capabilities, it would explain the increasing interception rates and the mysterious losses German bomber crews were experiencing. Professor Leo Brandt, Telefunken's senior microwave specialist, assembled Germany's best radar engineers to examine the captured AI Mark 8 equipment. The team worked through the night of May 3rd and 4th, documenting every component before attempting to power the system. What they discovered in those initial hours fundamentally challenged German understanding of practical radar engineering. The magnetron at the heart of the British radar was a copper cylinder, approximately 8 centimeters in diameter, containing 8 precision-machined resonant cavities, arranged symmetrically around a central cathode. Powerful permanent magnets were integrated directly into the assembly. The device was compact, robust, and appeared to be production hardware rather than experimental prototype. When the German team powered the magnetron using improvised test equipment, it generated approximately 10 kilowatts of pulsed power at 9.1 centimeter wavelength. The output was stable, repeatable, and far exceeded anything German magnetron research had achieved. Dr. Otto Hachenberg, a young Telefunken engineer assigned to the examination team, would later recall the moment of realization in interviews conducted decades after the war. "We were examining equipment that proved British engineers had solved problems we had declared impossible based on theoretical analysis. The power output at that wavelength contradicted our mathematical models. We understood immediately that German night bomber operations over Britain were facing capabilities we hadn't known existed. British Nightfighters could see our aircraft in darkness using radar we couldn't detect and technology we couldn't match." The captured equipment revealed multiple layers of British engineering superiority. The receiver used crystal mixers and intermediate frequency amplifiers, with sophistication exceeding German practice. The display presented targets in a plan position indicator format, a map-like representation far more intuitive than the A-scope displays German systems used. The antenna rotation mechanism was elegant and reliable, designed for operational durability rather than laboratory demonstration. Every aspect of the system indicated mature engineering refined through extensive production experience. This was not experimental equipment hastily deployed. This was third or fourth generation technology, implying British radar development had progressed through multiple improvement cycles, while Germany remained focused on longer wavelength systems. The tactical implications were immediately apparent to every German engineer and officer who examined the equipment. British Nightfighters equipped with AI Mark 8 possessed detection ranges approaching 8 kilometers, roughly double German Lichtenstein capability. The centimetric wavelength provided angular resolution, allowing distinction between individual aircraft in formation. The narrow beam width enabled accurate bearing measurement. Most critically, the 9.1 centimeter emissions were completely undetectable by German radar warning receivers designed to sense longer wavelength transmissions. German bomber crews flying over Britain had no warning that they were being tracked until British fighters opened fire. General Lieutenant Josef Kammhuber, commanding German night fighter forces, received the technical briefing on May 10th. Kammhuber had built the Himmelbett line and developed the tactical doctrines that had made German night fighters increasingly effective through 1941 and 1942. He understood immediately that British technological advantage had fundamentally altered the tactical balance. German bombers over Britain were now the hunted rather than hunters, visible to enemies they couldn't detect, tracked with precision German crews couldn't match. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The question facing German leadership in May 1943 was stark. How widespread was British centimetric radar deployment, and could Germany develop effective countermeasures before losses became unsustainable? Intelligence assessment suggested British production was substantial. Multiple intercepts of centimetric radar emissions indicated numerous aircraft were equipped. Interrogation of captured RAF crew members, conducted carefully to avoid revealing German knowledge of the radar, confirmed that AI Mark 8 was standard equipment on Mosquito night fighter squadrons, with production continuing at rates suggesting eventual deployment across the entire night fighter force. German countermeasure development faced immediate obstacles. Detecting centimetric radar emissions required receivers tuned to frequencies. German electronics industry had minimal experience manufacturing. The components needed crystal mixers, waveguide sections, antenna elements were unfamiliar to German manufacturers oriented toward longer wavelength systems. Even conceptually straightforward devices like radar warning receivers for centimetric wavelengths would require development time measured in months. Telefunken engineers began immediate development of a radar warning receiver designated Fug 350 Naxos, designed to detect British centimetric emissions. The system used a rotating directional antenna housed in a teardrop-shaped fairing mounted on aircraft fuselages. The receiver covered frequencies from 2.5 to 3.75 GHz, encompassing the operating range of British AI Mark 8 radar. Detection range was estimated at approximately 35 kilometers under optimal conditions, theoretically providing bomber crews with warning before British fighters could complete interceptions. But developing prototype receivers proved vastly easier than production deployment. Naxos required components the German industry struggled to manufacture consistently. Crystal detectors operating at centimetric wavelengths needed germanium crystals ground to precise specifications and contacted with extreme care to create proper semiconductor junctions. German manufacturers had limited experience with these techniques. Waveguide components required machining tolerances tighter than standard German practice. Even coaxial cables designed for centimetric frequencies were in short supply, with German cable manufacturers oriented toward lower frequency applications. Material shortages compounded technical challenges. Naxos receivers required cobalt for magnet assemblies, but Germany faced critical cobalt scarcity, affecting all high-temperature alloy production. Copper for waveguide construction competed with munitions production. Aluminum for antenna elements was allocated primarily to aircraft manufacturing. Every material needed for Naxos production was simultaneously required for dozens of other military programs, each with compelling priority claims. German planners faced impossible allocation decisions that pitted defensive electronics against offensive weapons, aircraft production against radar manufacturing, immediate combat needs against longer-term capability development. Even as German engineers worked desperately on countermeasures, intelligence accumulated suggesting British centimetric radar deployment extended far beyond Nightfighters. Coastal Command aircraft hunting U-boats used ASV Mark III radar operating at similar wavelengths, explaining mysterious submarine losses in the Atlantic. British bombers carried H-2S ground mapping radar using the same cavity magnetron technology, providing navigation capabilities that rendered darkness and weather irrelevant. British ships mounted Type 271 surface search radar, detecting submarines and surface vessels with precision longer wavelength systems couldn't match. Each application represented mature operational deployment, not experimental testing. Britain had developed an entire family of centimetric radar systems, while Germany remained convinced such technology was impractical for military use. The scope of British achievement became clearer as more intelligence arrived through various sources. American forces entering the war had adopted British cavity magnetron technology with enthusiastic industrial mobilization. The radiation laboratory at MIT, established specifically to develop radar systems using magnetron technology, had grown to over 4,000 scientists and engineers by 1943. American electronics manufacturers, Western Electric, General Electric, RCA, Westinghouse, were producing magnetrons by thousands monthly, equipping American forces and supplying Britain through Lend-Lease. The disparity in production capacity was staggering. While German industry struggled to manufacture crystal detectors for warning receivers, British and American factories produced complete radar systems by hundreds weekly. The human dimension of this technological disparity manifested in climbing loss rates that told a story. German bomber crews understood viscerally, even if high command was slow to acknowledge. Luftwaffe bomber operations over Britain in early 1943 encountered night fighter interceptions at rates that made missions progressively more costly. Aircraft simply disappeared, their crews never reporting enemy contact, suggesting attacks that occurred without warning. Survivors who managed to evade attacks described British fighters appearing from darkness with impossible precision, positioning perfectly for attack runs that indicated prior knowledge of German bomber locations and altitudes. Oberfeldwebel Ernst Wagner, a Heinkel He 111 dorsal gunner who survived 3 separate night fighter attacks during April 1943, provided detailed testimony during operational debriefing that captured the psychological impact of fighting enemies with superior detection capabilities. The Tommies found us in complete cloud cover, where visual detection should be impossible. No searchlights illuminated us, no flak indicated our position, yet British fighters intercepted us with precision, suggesting they knew exactly where we were flying. Our Funkmessgerät gave no warning. The first indication of attack was cannon fire tearing through our fuselage. We were blind while they could see us clearly. There is no defense against enemies you cannot detect until they're killing you. German tactical adaptation attempts proved largely futile against technological advantage of this magnitude. Luftwaffe commanders ordered bomber formations to vary altitudes randomly, hoping to complicate British interceptions. They instructed crews to fly evasive courses rather than straight navigation tracks. They reduced formation sizes to minimize radar signatures. None of these adaptations proved effective against British Nightfighters that could detect individual aircraft at ranges exceeding visual distance by orders of magnitude, track them continuously, and position for optimum attack regardless of evasive maneuvers. The fundamental problem was that German bombers remained visible on British radar regardless of tactical innovations. A Heinkel He-111 presented a radar cross-section of approximately 15 to 20 square meters. British AI Mark 8 could detect such targets at 7 to 8 kilometers. No amount of tactical maneuvering could eliminate that basic detectability. German crews were attempting to hide from electromagnetic radiation using flight maneuvers designed for visual concealment, a conceptual mismatch between threat and countermeasure that rendered defensive tactics largely ineffective. German night fighter forces faced a mirror image of this technological asymmetry when engaging RAF bombers over Germany. While German ground control interception using Würzburg radar remained effective, British bombers were increasingly difficult to intercept as they deployed electronic countermeasures that exploited German radar's longer wavelength limitations. The introduction of window metallic chaff that created false radar returns in July 1943 devastated German ground control effectiveness. Each British bomber released bundles of aluminum strips cut to half wavelength of German radar frequencies. The chaff clouds created radar returns indistinguishable from aircraft, saturating German radar displays with false targets that made tracking individual bombers nearly impossible. The chaff countermeasure succeeded specifically because German radar operated at longer wavelengths. Disrupting 53 cm Würzburg radar required strips only 26.5 cm long, easily manufactured from standard aluminum foil. Disrupting 9.1 cm British radar would require 4.5 cm strips, vastly more difficult to deploy in quantities sufficient to create effective jamming. The physics worked in favor of the side using shorter wavelengths. British centimetric radar was inherently more resistant to chaff countermeasures than German longer wavelength systems. German night fighter crews suddenly found themselves in the same position as their bomber counterparts over Britain, fighting enemies with superior detection capabilities, while their own radar became progressively less effective. Lichtenstein AI radar, already limited by its 4-kilometer maximum range and complex antenna drag, became nearly useless against bomber streams employing window. The radar displays are filled with false returns, making real target detection impossible amid the electronic clutter. General Major Josef Schmid, commanding the 1st Fighter Corps responsible for Reich air defense, watched the defensive system that had taken years to build collapse within weeks of Window's introduction. Loss rates for German night fighters actually increased as pilots pressed attacks without effective radar guidance, relying on visual acquisition that British bombers' defensive gunners exploited ruthlessly. The integrated Himmelbett system, carefully developed through 1941 and 42, became nearly worthless overnight. German night fighter effectiveness, measured by bomber kills per sortie, dropped by approximately 70% in August 1943 compared to June. Luftwaffe technical services scrambled to develop countermeasures against window, but the solutions were not straightforward. Simply changing radar frequencies provided only temporary relief before British intelligence detected the new frequencies and adjusted chaff dimensions accordingly. The fundamental answer was shorter wavelength radar resistant to chaff jamming, but that meant developing the centimetric radar technology Germany had neglected for years. German engineers were attempting to replicate in months what British researchers had spent 3 years perfecting, while simultaneously dealing with Allied bombing disruption, material shortages, and competing priority demands from other military programs. The Naxos radar warning receiver finally entered operational service in September 1943, 5 months after the Rotterdam capture provided definitive evidence of British centimetric radar. The delay illustrated the industrial and technical challenges Germany faced even deploying conceptually straightforward detection equipment. Production rates remained limited by component shortages and manufacturing bottlenecks. Initial installations went to bomber units operating over Britain, providing crews with at least theoretical warning of British night fighter radar emissions. Operational results were mixed at best. Naxos could detect British radar at useful ranges when it worked properly, but the system suffered reliability problems that plagued early production units. The rotating antenna mechanisms jammed frequently, receiver sensitivity degraded rapidly under operational conditions. False alarms from friendly radar emissions confused crews. Most critically, detection of British radar provided warning but no capability to evade interception. British night fighters with superior speed could pursue German bombers even when detected. A warning receiver told German crews they were being hunted but offered no solution to the fundamental problem that British fighters could track them continuously using radar German bombers couldn't counter. Some Luftwaffe bomber crews developed desperate tactics based on Naxos warnings. When British radar was detected, crews would dive to low altitude, hoping to break radar contact or force British fighters into dangerous low-level pursuit. Others attempted radical evasive maneuvers, tight turns, altitude changes, speed variations trying to shake tracking. These tactics occasionally succeeded but more often simply delayed the inevitable. British night fighter crews with superior radar could reacquire targets after evasive maneuvers, patiently stalking German bombers until positioning for successful attacks. The psychological impact on German bomber crews was profound and measurable through rising abort rates and declining mission effectiveness. Crews who had flown confidently through darkness now understood they were illuminated on enemy radar screens, tracked with precision, hunted by fighters they couldn't detect until cannon fire announced their presence. The stress of knowing you're being stalked by invisible enemies eroded crew morale more effectively than actual combat losses. Men developed psychosomatic symptoms, tremors, hyperventilation, inability to concentrate that medical officers recognized as combat fatigue but couldn't effectively treat because the source wasn't physical injury but technological helplessness. Hauptmann Werner Barke, a Junkers Ju-88 commander who completed 37 missions over Britain before his crew was shot down in December 1943, later described the psychological burden in interviews conducted while a prisoner of war. Flying over England became suicide missions disguised as combat operations. We knew British fighters could find us in any weather, any darkness. Our Naxos gave warning sometimes, but warning without solution creates only additional stress. We flew each mission knowing that invisible enemies tracked our every movement. The psychological pressure of being hunted by forces you cannot counter is worse than direct combat, where both sides face equal dangers. We were not fighting. We were waiting to be killed by enemies who possessed overwhelming technological advantage. German attempts to develop indigenous centimetric radar proceeded in parallel with countermeasure development, but progress remained frustratingly slow as Germany's strategic situation deteriorated. Telefunken worked on an airborne interception radar, designated Fug 240 Berlin, using cavity magnetron technology reverse-engineered from captured British equipment. The development faced identical material and manufacturing constraints that plagued Naxos production. Magnetrons required cobalt for permanent magnets, precision machining for resonant cavities, specialized cathode coatings. Germany struggled to manufacture consistently. Each component represented development challenges requiring time and resources. Germany increasingly lacked. The Berlin radar program revealed another dimension of German technological disadvantage. Even when German engineers understood British technology conceptually, they lacked the manufacturing infrastructure and production experience to replicate it at scale. Telefunken could build laboratory prototypes that functioned comparably to British radar. Moving from prototype to production units manufactured consistently with reliable performance required industrial capabilities Germany hadn't developed. British magnetrons came off production lines with guaranteed specifications because manufacturing processes ensured consistency. German magnetrons required individual tuning by skilled technicians, a laboratory approach fundamentally unsuited to military production scale. By mid-1944, Telefunken had delivered approximately 15 Fug 240 Berlin radar sets for operational testing. These equipped select Junkers Ju-88 Nightfighters operating in Reich defense. Performance was broadly comparable to British AI Mark 8 from 1942, representing technology Britain had fielded operationally 2 years earlier. German centimetric radar in 1944 matched British capability from mid-war, while British systems had progressed to even shorter wavelengths and more sophisticated signal processing. The British, aware from signals intelligence that Germany was developing centimetric radar countermeasures and indigenous systems, had already moved to next-generation technology. AI Mark X radar operating at 3 cm wavelength entered service in late 1943, providing superior resolution and resistance to German countermeasures. The 3 cm wavelength required even more sophisticated magnetron designs and manufacturing techniques, but British industry had developed the expertise through years of continuous production. By the time Germany deployed 9 cm radar, Britain operated systems at 3 cm, maintaining a technological lead that Germany couldn't close. American radar development paralleled British programs with industrial mobilization that dwarfed both British and German efforts. The SCR-720 airborne interception radar, developed by the Radiation Laboratory and manufactured by Western Electric, equipped American Nightfighters in Europe and the Pacific. American production capacity enabled deployment at scales German industry couldn't approach. By mid-1944, American factories produced hundreds of complete radar systems, monthly across multiple types: airborne interception, ground mapping, surface search, fire control, each representing sophisticated electronics manufactured to consistent specifications with reliable performance. The cumulative effect of British and American centimetric radar deployment across all combat theatres created tactical advantages that influenced virtually every aspect of air warfare. RAF Bomber Command navigated and bombed through weather that would have scattered earlier raids. Coastal Command hunted U-boats with effectiveness that forced Kriegsmarine to withdraw submarines from the Atlantic. Allied night fighters decimated Luftwaffe bomber forces attempting attacks on Britain. American strategic bombing of Germany proceeded regardless of weather conditions, with H-2X radar allowing target identification through solid overcast. Each capability derived from cavity magnetron technology that enabled compact, powerful centimetric radar systems Germany couldn't match. German bomber operations over Britain became progressively unsustainable through late 1943 and into 1944 as British nightfighter effectiveness reached levels that made strategic bombing operationally impossible. Loss rates exceeding 10% per mission were not sustainable, given Luftwaffe training capacity and aircraft production rates. Experienced crews were dying faster than replacement training could provide. New crews, hastily trained with reduced flying hours, died on first or second missions before acquiring experience necessary for survival. The technological advantage British centimetric radar provided had operational consequences that transcended simple kill ratios, destroying the institutional knowledge and experience base that effective bomber forces required. Operation Steinbock, the baby blitz conducted from January through May 1944, represented Germany's final sustained bomber offensive against Britain. The operation committed approximately 470 bomber aircraft to nighttime attacks on London and other British cities, attempting to divert Allied resources from preparations for invasion and to demonstrate that Germany retained offensive capabilities despite 3 years of defensive warfare. The results validated every assessment of British technological superiority that German intelligence had compiled. During 4 months of operations, Luftwaffe bomber forces flew approximately 2,200 sorties and dropped approximately 2,300 tons of bombs on British targets. These attacks killed approximately 1,600 British civilians and caused disruption, but strategically, Steinbock achieved nothing approaching its objectives. More critically for Luftwaffe bomber forces, German losses during the operation were catastrophic. Approximately 330 aircraft were destroyed, roughly 70% of committed forces. Loss rates averaged 15% per mission, completely unsustainable for continued operations. British Nightfighters equipped with AI Mark X radar accounted for the majority of German losses. RAF Fighter Command squadrons flying Mosquito Nightfighters achieved interception rates that German tactical planners had considered impossible. The combination of ground control interception guidance, improved radar, and superior aircraft performance created killing fields over Britain, where German bombers operated at overwhelming disadvantage. Luftwaffe crews nicknamed the missions Himmelfahrt Kommandos, heaven-bound missions, acknowledging that most crews wouldn't return. Oberst Dietrich Peltz, commanding the IX Fliegerkorps responsible for Steinbock operations, watched his bomber force disintegrate under losses that couldn't be sustained. Unit after unit was pulled from operations after losing 60 to 70% of aircraft and crews. Replacement aircraft arrived from factories, but replacement crews with sufficient training and experience didn't exist. The Luftwaffe training system, strained by losses across all theatres, couldn't produce bomber crews fast enough to replace combat losses. By May 1944, German bomber forces in Western Europe were effectively finished as strategic threat, withdrawn from offensive operations and reassigned to other roles or disbanded entirely. The operational impact of British technological advantage was measurable in statistics that told the story of systematic destruction. German bomber strength in Western Europe declined from approximately 470 operational aircraft in January 1944 to roughly 130 by June. Of the 340 aircraft lost, approximately 220 were confirmed destroyed by British Nightfighters, validating the decisive advantage centimetric radar provided. The remaining losses included accidents, mechanical failures, and anti-aircraft fire. But Nightfighters accounted for 2/3 of total attrition. Individual squadron histories illustrated the human cost of technological disparity. Kampfgeschwader 54, operating Junkers Ju-88s from bases in France, began Steinbock with 42 aircraft and 168 crew members. By April 1944, the unit had lost 31 aircraft and 124 crew killed or missing, representing 74% aircraft losses and 74% personnel casualties in 3 months. The survivors, men who had watched their comrades die in nightly operations, understood they were participating in futile operations where technological inferiority rendered courage and skill insufficient for survival. Feldwebel Kurt Eismann, a radio operator in KG-54 who survived the campaign despite flying 23 missions, later described the experience in testimony recorded during post-war interviews. Every mission, we watched aircraft disappear from formation without warning. No radio calls, no flares, simply gone. We knew British fighters were killing them using radar we couldn't detect. Our Naxos sometimes gave warning, but knowing you're being hunted doesn't help when the hunter possesses superior weapons and speed. We flew because orders demanded it, but we understood we weren't accomplishing military objectives worth the losses we suffered. The British had technology we couldn't match, and that technological advantage killed more crews than any tactical factor. The parallel story in German night fighter operations defending the Reich showed similar technological disadvantage, though defensive mission requirements provided tactical options that offensive bomber operations didn't allow. German night fighters could operate from established airfields with ground control support, rely on searchlight cooperation, and exploit defensive advantages of fighting over friendly territory with rescue available for downed crews. These factors mitigated but didn't eliminate the disadvantages arising from inferior radar technology. The introduction of window in July 1943 had devastated German ground control effectiveness, forcing tactical adaptations that partially restored interception capability. Luftwaffe night fighter forces adopted new tactics collectively called Wild Sow Wild. Bohr, where single-engine fighters operated independently without ground control, using visual acquisition enhanced by searchlight illumination and fires from bombing to locate British bombers. The tactic worked temporarily, achieving success through mid-1943, but it was fundamentally limited by dependence on visual conditions and proximity to illuminated target areas. Zami-Sao tame bore tactics represented a more sophisticated adaptation, where twin-engine Nightfighters operated with reduced ground control dependence, using airborne radar to locate bombers independently within broad patrol zones. This required improved airborne radar systems, resistant to window jamming. German engineers developed Lichtenstein SN2 radar, operating at lower frequencies specifically to avoid window jamming tuned to earlier radar wavelengths. The SN2 operated at approximately 90 MHz, corresponding to 3.3 meter wavelength, far too long for typical window chaff to jam effectively. But operating at lower frequency created new problems that illustrated the fundamental physics constraining radar design. The 3.3 meter wavelength required enormous antenna arrays to achieve useful directivity. The SN2 used Hershkovai Stag's antlers antenna, consisting of 8 dipole elements arranged in a complex array projecting from the Nightfighter's nose. This array was even larger and created more aerodynamic drag than the Matratze array it replaced. Aircraft equipped with SN2 suffered speed reductions of 40 to 50 km per hour, making interceptions of faster British bombers increasingly difficult. The performance penalties of larger antennas illustrated the fundamental advantage shorter wavelength radar provided. British AI Mark X, operating at 3 cm wavelength, achieved superior resolution with antenna barely 70 cm in diameter, creating negligible aerodynamic drag. German SN2 radar, requiring massive antenna arrays to achieve comparable performance at meter wavelengths, demonstrated why centimetric technology represented revolutionary rather than evolutionary advance. The physics of electromagnetic propagation favored shorter wavelengths for virtually all tactical applications, and Britain's mastery of magnetron technology, enabling centimetric operation, provided advantages Germany couldn't overcome through tactical adaptations or engineering workarounds. German night fighter effectiveness recovered partially through late 1943 and early 1944 as new tactics and improved radar restored some interception capability. Major Heinz Wolfgang Schnaufer, one of Germany's most successful night fighter pilots, achieved 121 confirmed victories, despite operating with technically inferior equipment compared to British systems. His success, and that of other skilled pilots, demonstrated that tactical expertise and operational experience could partially compensate for technological disadvantage. But aggregate statistics showed that German night fighters faced increasingly unfavorable exchange ratios as British electronic warfare capabilities improved and American escort fighters entered the battle. By mid-1944, RAF Bomber Command operated with sophisticated electronic warfare suites that included window chaff dispensers, active radar jammers, and tail warning radars. The combination created an electromagnetic environment so cluttered and confused that German radar-based interceptions became progressively more difficult. British bombers that German fighters managed to intercept defended themselves with tail turrets armed with 4 Browning machine guns, forcing German fighters to approach from angles where visual acquisition was difficult and defensive fire was most effective. The arrival of American long-range escort fighters, P-51 Mustangs and P-47 Thunderbolts accompanying bomber formations deep into Germany, added another dimension to German night fighter challenges. While escort fighters were primarily protected against daylight attacks, their presence forced German fighter resources to be split between day and night defense. Units were pulled from night fighter operations to counter daylight raids, reducing forces available for nocturnal interceptions. The cumulative pressure across all defensive missions exhausted both aircraft and crews faster than training and production could replace losses. Generalleutnant Josef Schmid, still commanding Reich Air Defense through 1944, faced impossible resource allocation decisions, as American daylight bombing and British night attacks created relentless pressure that German defenses couldn't sustain. Fighter production increased dramatically through 1944, with monthly outputs reaching approximately 3,000 aircraft by autumn. But pilot training couldn't keep pace. Fuel shortages limited flying hours for replacement pilots. Experienced instructors were pulled from training units for combat operations, reducing training quality. New pilots arrived at operational units with 100 to 120 flying hours, compared to 250 to 300 hours for pilots trained in 1941. These undertrained pilots died quickly, killed by better-trained Allied pilots flying superior equipment with technological advantages German forces couldn't match. The technological advantage British centimetric radar provided wasn't decisive by itself. Wars are won through complex combinations of industrial capacity, strategic decisions, tactical execution, and numerous factors beyond any single technology. But centimetric radar represented a paradigmatic example of how revolutionary technology deployed at scale creates tactical advantages that influence operational outcomes across entire theatres. British Nightfighters with AI Mark 8 and later AI Mark X could operate in conditions where German fighters remained ineffective. British bombers with H-2S navigation radar could strike targets in weather that grounded earlier bombing efforts. Allied anti-submarine forces with ASV Mark III radar could hunt U-boats that previously operated with impunity in darkness. Each capability derived from cavity magnetron technology that Britain developed between 1940 and 1942, while Germany remained focused on longer wavelength systems. The British decision to prioritize centimetric radar development, made in desperate circumstances during 1940 when invasion threatened, created technological advantage that matured into operational superiority by 1943. Germany's decision to focus resources on near-term improvements to existing systems rather than long-term revolutionary technology meant Germany fought the radar war with previous generation capabilities against enemies, operating 1 or 2 generations ahead technologically. The human cost of this technological disparity was measured in thousands of German aircrew killed in operations where technological inferiority made survival increasingly unlikely. These were not poorly trained conscripts or obsolete forces. Many were experienced airmen, skilled pilots, trained operators who understood their equipment and tactics. They died because technological advantage provided enemies with capabilities German forces couldn't counter effectively. Courage, skill, and tactical expertise proved insufficient against adversaries who could see in darkness using electromagnetic eyes, while German forces remained essentially blind by comparison. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.